We're here today. I'm gonna grab my booklet. Right. Talking about the birth of 6PPD-Q soil extraction with Thomas Chontofalsky and Fatima Alsinai with the Center of Urban Waters in the city of Tacoma. My name is Kelsey Crane. I work for the community of Thurston County. Happy to be here with you all. Please silence your cell phone. This presentation is being recorded, as I'm sure you've heard. All of them are. And we're going to dive right in because it's almost lunch.
All righty. Everyone hear me, I'm assuming. Today's been a busy morning. It's been a lot of presentations. And so, yeah, how about we do this presentation and then we all do lunch after this? Is that cool? Okay. All right, let's rock and roll. All right, so the birth of the soil 6PPD extraction. Before we get into it, let me sort of set the scene. All right, so back in January 2024, 1634 just came out. Of course, that's the extraction and the water analysis for 6PPD-Q. And well, you know, I had our LC triple quad ready to go. I already had the quant method, had the acquisition method, even got a calibration, did a couple practice extractions. We were set to go. Now, I've been in this business for 20 plus years, so I usually know when a water extraction comes out, a soil extraction is short to follow. So I wanted to get a jump on things. I wanted to see what was coming down the pipeline. So I did what any scientist would do in this day and age. I Googled it. The thing is I saw some studies that had the relationship between 6PPD-Q and soil, you know, how it gets into the soil, how it binds with the soil, but I didn't see anything that was a quantitative soil extraction. So I thought, well, that's a challenge, but I like challenges, so I thought, why not? Let's see what I can create here. So as I was thinking about what to start with, all of a sudden word got out that the Department of Ecology was handing out money. Of course, this money was in the form of grants, and there was criteria that you had to meet in order to get this money. But I thought a soil extraction for 6PPD, sure, they're gonna like that. So we submitted. They said yes, we said yay. And we were funded. Now, of course, all these important things that we could get with this money, the most important thing that enabled us to do was to hire a very talented, very intelligent chemical engineer graduate who just so happens to be standing to my right now. This is Fatima. And so after about a week of working together, you know, she was originally signed on as like an assistant to me, but after about a week of working together, and she tolerated my sense of humor, and I thought, wow, this is going to be something else. I looked at her and said, let's just be partners on this. Let's combine our talents. Let's change the way the world sees soil 6PPD-Q. And so with that said, the great words of Paul Harvey, and now here's the rest of the story. So what do we have on the menu today? See, I'm already thinking about lunch, but here's what we have. Okay, we're going to be doing a 6PPD to 6PPD-Q introduction. Of course, I know you've heard it a million times this morning, but you know, we don't want to feel left out, so we're going to do it too. We're going to come up with a purpose. We're going to tell you about the purpose, what drove us to want to do a soil 6PPD extraction. Then we're going to kind of take a turn here, and we're going to actually turn this into a training. We're going to talk about all the materials that we used. We're going to go through the way we actually do the 6PPD soil extraction. So you're going to learn that. Then we're going to do a little overview of how this is being analyzed on our LC. We're going to go through results and discussion, how our 6PPD soil extraction worked, and of course, a conclusion. Now on the last slide, there's going to be a QR code. So everything we're talking about today, about this SOP, this method, you can go to the QR code and it's going to access, you're going to have access to the SOP to this method. So most of the stuff that you're going to see later on, you pretty much have it in your lab if you do have a lab or you know of one. A lot of the stuff you're going to see. So does that sound good? All right, let's get into it. Let's do the introduction. Fatima?
So, as many of you guys already know, 6PPD-Q is an oxidation transformation byproduct of 6PPD. It's a commonly used antioxidant in rubber products. It leaches into soil when tidal wave particles are carried into stormwater systems. Is this better? Yes, because, okay. When it's carried into stormwater systems, and there it's rapidly oxidized to 6PPD-Q. We realize that it strongly binds to sediment matrices for long periods of time, and it's likely due to the high optimal water partition coefficient. The purpose of this project was to understand the interaction between 6PPD-Q and soil, and we wanted to evaluate the persistence and absorption behavior. And by accurately quantifying its concentration in sediments, we hope to support development of regulatory standards and risk assessment frameworks. Additionally, we hope this data benefits engineers and scientists who are trying to develop treatment processes and methods to destroy 6PPD-Q. And lastly, we hope to, our lab hopes to use this data and information gathered to find a way to treat or destroy 6PPD-Q.
All right, well, let's get into the materials and the methods. First of all, you need a solvent. You need to get it out of the soil somehow. What you see up here is a mixture between hexane and ethyl acetate. Later on, I'll get into how we got to that point. The soil media for the SRM, we actually created a standard reference material because you can't buy one at any vendors. We happen to use bentonite clay powder. Okay, so then the next three compounds we're going to be using to test the EIS, which is like the surrogate extracted internal standard. All of these come in at like 100,000 ppb, so of course you're going to have to dilute down to what these are. The second one should say D5. 6PPD-Q, but it says 13C, but just ignore that. But that's actually going to be a 20 ppb spike that we have, and that's going to be our internal standard. It's the NIS, so you're not extracting, just injecting it. And then the star of the show, 6PPD-Q, took it from 100,000 down to 1,000. And the standard SRM, the standard reference material, what I wanted to do with this is, I know a lot of extraction methods, what they usually do is take a little bit of audible sand, spike it with a compound, and then take it through. To me, that's good, but I wanted to emulate what was going on out in the real world. And so what we did is we took the bentonite clay, since it's very, very easy to work with, spiked it with the 6PPD-Q. In our case, we did 25 ppb, put a little ethyl acetate in it, vortex it to homogenize it, and it simply just let the ethyl acetate evaporate off. And then what we have, now we have a gram of what we used a gram. Now we have a gram that we can take any little portion of, and it should come out, calculate out to 25 ppb.
And you'll need 0.25 grams of sample. We decided to use a small sample size because sometimes the city of Tacoma gets a small sample, so we have limited supply. And you'll need a vertexer, an ultrasonic cleaner, and then a nitrogen evaporator, also known as an NVAP. Now I'm going to walk you through the procedure. First, you're going to weigh out your 0.25 grams of sample into a 12 ml or 8 ml in glass vial. You just can't use any, is it poly? Right?
Pretty much any plastic.
Yeah, so just make sure it's glass. Then you're gonna spike it with that 200 ppb EIS at 10 microliters. Then you're gonna you're gonna add 0.5 mils of ethyl acetate and 4.5 mils of hexane. Then to start the release of 6PPD-Q, you're gonna quickly vortex your sample. And then to enhance that mass transfer and further desorb 6PPD-Q, you're gonna sonicate it for 30 minutes. After sonication, you're gonna wanna separate that liquid and solid phase. So you're gonna centrifuge for 5 minutes at 2000 RPM. Then you're gonna carefully pour in your approximate 5 mils of solvent into a new 12 mil amber glass vial. If you think you could spill it, you can also transfer it using a pipette. I just prefer manually transferring. Then you're gonna place your sample under an N evap, and you're gonna wait until the solvent is completely dry. After you're gonna re-elute, I think we had sent in an edited version of this, but it didn't make it. You're gonna re-elute with 1 mil of acetonitrile, then you're gonna vortex and sonicate for 2 minutes to make sure all of that 6-PPD-Q is not sticking onto the glass and is really in your solvent. Then you're gonna spike it with the IIS at 10 microliters. Then you're gonna subject it to analysis.
Okay, so for the analysis, again, we have a 6470 Agilent LC triple quad. For the mobile phases, if anyone does soil, or excuse me, the water 6PPD analysis, it's pretty much you're gonna see something that's similar up there. You're gonna see an acetonitrile with formic acid for the organic mobile phase, and then for the water, normally it's DI water with a little bit of, well, the milk or fancy stuff. DI water with a little formic acid, but in this case, we are actually adding ammonium acetate to it. Now, if anyone runs, I know this is off topic, but if anyone analyzes PFAS, that would look familiar because that's the same amount of ammonium acetate that you use in the water one. That's just a trivia question for later. And then here, the column that we're using, I actually use a Agilent PowerShell 120. For those who don't know what that means, it's a C18 reverse phase silica base, and if you don't know what that means, it's a stick that I put in it. Anyways, so then the flow gradient, it's a pretty quick method. I mean, it goes through, it's about 5 minutes with a minute post time, so it's about a 6 minute per sample. It just speed right through it. One thing that I don't have up there is the calibration. Our calibration for both water and for soil goes from 0.01 ppb up to 100. It's a wide range, but the RSC for linearity is about like 3 to 4. So I mean, it's pretty dead on.
So after method development and optimizing many parameters, we were able to develop a way to create a reference material in-house that mimics the natural occurrence. And we validated our method against linearity, precision, and accuracy at 2 fortification levels and showed satisfactory recoveries within that range, 70 to 130%.
All right, and then like we mentioned before, we were able to use a small amount. We have these sediment, the city of Tacoma has these sediment projects. They're great projects, but sometimes, you know, the bank's kind of low. We don't really get that much soil sediments. And so to be able to use 1/4 gram is huge. At least we're able to extract it and actually run the analysis. And then speaking of a sediment sample project, we just successfully applied this to a project that we're working with Ecology and Pereira with, so it works. All right, so when we're coming back to the solvent thing, originally we used acetonitrile only because that's what I make up the calibration standards with. But we wanted to use, anyone that works with acetonitrile knows that it evaporates really, really slow. So since we're trying to evaporate to complete dryness, it's a long time. So we thought about, well, what's the fastest evaporating solvent out there? Acetone. Acetone was great in the beginning, but as soon as we got this sample, 56.9 is like the nasty sample that we have. When we got to real life samples, it was extracting both 6-PPD and some other polar interferences. So we thought, well, this is a nonpolar compound. Why don't we use a nonpolar solvent? Switch to hexane. Hexane, this is the same exact sample. You can see the difference between all the junk on top and no junk on the bottom. Okay, so once we were using hexane, we thought, cool, we are off to the races. And we went back to our bentonite clay SRM. So when we were using that, well, bentonite clay is a polar soil media. So hexane alone was just not doing it. Wasn't cutting it to get back to the SRMs and the MRLs and all the other stuff. So what we had to do is, I thought back to like Greek mythology, the thing called the Trojan horse. Well, what happens is, the Trojan horse was left and they brought it into the gates. They thought it was a gift. At nighttime, all the soldiers came out, let the rest of the boys in and took off and did what they had to do. This ethyl acetate is our Trojan horse. You mix a little bit in, it goes into a polar, non-polar, it doesn't matter, it goes into the soil media. As soon as it gets in, gets let in the gate, the hexane gets in there and does what it's supposed to do. Also, the other thing we found out is diluents are popular amongst all different kind of extractions. PFAS has a whole stew of things that you gotta put together just to have the PFAS diluent. For this one, we needed a soil diluent for our soil extraction because there was something that the soil was doing to the acetonitrile that just wasn't quite right. So we had to make it a matrix matched diluent, but it's so simple. All you do is you take a little bit of bentonite clay in our case, put about 10 mils of acetonitrile in it, vortex it, spin it down, take the supernatant off it. Bada boom, there you go, there's your soil diluent.
And even with matrix matching, we still found that the IIS was being suppressed. So that's when we decided to use that ammonium acetate salt in the MOLA phase. And then when we performed our method detection limit study, we saw an increase in IIS recovery. This bar plot shows the EIS and the IIS recoveries across the 28 stormwater sediment samples. As you can see, about 70%, more than 70% of the samples recovered within range. However, the variation is probably due to the heavy oils in the samples or the hydrophobic matrix components. Additionally, I used the Pearson correlation, and you can see here the R value is negative 0.727, which is very close to -1. So the correlation, we observed that as one standard increases, the other decreases is proven at the 95% confidence interval.
And then as you can see here, this is basically what we found out there. So the green represents the levels of 6-PPD. As you can tell, the highest one that we've had is almost 700 ppd. There's a lot of 6-PPD-Q out there. So hopefully this is an eye-opener for people that, hey, it is out there, like it's really out there. So with this data that we were able to do, hopefully we can, gain more education on what we're doing. We could kind of make projects to kind of combat this and undo what they've done before.
So to conclude, we were able to develop a very simple, fast, and efficient method to quantify 6-PPD-Q from various solid matrices, only using a small sample size.
And then we also showed that this choice of solvent plays a huge role to whether you can extract the compound or extract a bunch of stuff you don't want. The ratio that we had was just enough to where it could take it from even a polar compound. I actually used it on like biosolids, and if anyone knows what biosolids is, it's real nasty. I tested it, there was nothing in there, but it's still, the EIS came out within, acceptance range, so did the IIS. So wide range by making a mixture like this.
We also tried employing solid phase extraction cleanup methods, but that did not improve the IIS recovery or clean up any of the matrix interferences we were having. So we decided not to further test any, but we decided to test fluorosil, and we did a preliminary study, and it kind of improved it. But we need further research into this. And I did write a report to the Department of Ecology that should be up on the page sometime soon that has details about this research.
So hopefully with the data that we came up with for the soil extraction, we can maybe one day actually treat like 6 PPD, like destroy it. There's a lot of bioretention and or ways to retain it, pull it out of the water, but maybe we can destroy it from that soil, so. All right, like I promised, this is the QR code. If you want to take a picture of it, our contact information is down there. Feel free to access the SOP, give it a shot. If you have any problems, just contact us and we'll walk you through it. Are there any questions?
We have tested biochar and it kind of eats up the surface standard. So we can use that as a.
Yeah, in the beginning, we used diatomaceous earth, we used auto sand, of course, we used a mixture of all these different kinds. But yeah, bentonite clay is not the one and only. There are other ways to do it. We just haven't gotten around to keep testing it because we have a project to meet.